This is our first discussion on equilibrium, and so we're going to focus mainly on the conceptual aspects. Chemical equilibrium is what occurs when our concentrations of the reactants and products remain constant with time. Okay, and so this may seem a little confusing because up to now we really haven't talked about reactions that don't go to completion. Okay, most of the things that we deal with, we look at the reactants combine, and when we run out of one of them, then the reaction stops. And so we have products, and then we have our excess reactants left over. Well, that's not always the case, and especially where we have our reactants and products isolated. Okay, our system is isolated from the surroundings. And so what we would see happening is, okay, we have our reactants forming products. Okay, that's what we're familiar with. But what happens is that at some point, the concentration of the products becomes sufficient for the products to start recombining or rearranging to form reactants. So the reverse reaction, okay, we call that the reverse. This is forward. Okay, so the forward reaction begins, and at some point it starts to reverse, and we have both of these going on simultaneously. And then at some point, the rate at which it is proceeding in the forward direction and the rate at which it proceeds in the reverse direction are equal. And at that time, the concentrations of the reactants and the products will no longer change. We call that chemical equilibrium. So the other thing to remember, like it says here, is that even though it macroscopically appears that nothing is changing, that actually on the molecular level, the forward reaction and the reverse reaction are still occurring. It's just that they are occurring at the same rate. Okay, we kind of have talked a little bit about this before, but that reaction rate depends on concentration. So if you think about it, the more reactant particles I have, the greater the probability of collisions of the reactants so that the reaction can occur. So more collisions, faster rate. Higher concentrations means we have a higher probability of collisions. So we're going to look at, now in a graph form, we'll make it a little easier. Let's look at, here we have a forward reaction, and I don't know why this has got a single arrow. This should actually look like that rather than that arrow there. Okay, so we have a forward reaction. We have the water, carbon monoxide combining together and forming hydrogen gas and carbon dioxide. So as you would expect, as the reaction proceeds, the concentrations of the water and the carbon monoxide are going to decrease because we're using them to make our products. And here our product concentration is increasing. And then at some point here, the reverse reaction starts to occur. And so the CO2 and the hydrogen gas recombine, start making reactants. And so at that point, which we have a little dashed line here to show that point, the concentrations will stop changing because we are creating products and recreating reactants at the same rate. Okay, so let's look at it. Here's another graph showing the actual rates and what's happening to the rates. So as the reaction starts, the rate of the forward reaction is at its highest at the beginning because that's where the concentrations of the reactants are the highest. So then as we use up the reactants, the rate decreases and slows down just like it's shown here. And then as the concentration of the products increases, the rate of that reverse reaction is going to start increasing. And then again, at some point, the rate of the forward and the rate of the reverse will be equal, and at that point we will have equilibrium. Okay, so here's another one. This is a Haber process. This is the way that they basically take nitrogen out of the atmosphere and are able to use it to make many, many useful things. Very important process here. And so if we look at the Haber process, where we're combining nitrogen and hydrogen to make ammonia, all right, initially our two reactants, concentrations start to decrease. There's our hydrogen, there's our nitrogen, and products start to increase. Now, one of the things to note here is that at equilibrium, it doesn't mean that the reactant and product concentrations are equal. Okay, the concentrations themselves are going to vary. In this case, we see that at equilibrium, we have a higher concentration of the hydrogen than we do of the ammonia or the nitrogen. So equilibrium is just meaning that the rate at which the reactions are proceeding are the same. But the actual concentrations at equilibrium are not equal to each other. Okay, so how do we know what the concentrations are going to be at equilibrium? Well, that's where a thing called the equilibrium expression comes in. And what this is the relationship or a way to show the ratio between the product concentrations and the reactant concentrations. And so this expression, the law of mass action, is what is used to write this equilibrium expression. We use the letter K for the equilibrium constant. That defines that ratio. And so you'll notice that when we use this law of mass action, we do products. It's products over reactants. And if in the balanced equation, if it has a coefficient, then we're going to raise the concentration to that power. Okay, so let's look at an example. Say I have this expression here, and we wanted to write the equilibrium expression for that. We could write that it's equal to, okay, products. So I have my nitrogen dioxide to the fourth, the water to the sixth, over the reactants, which I have the ammonia to the fourth and oxygen to the seventh. Okay? These are, as typical, we can express these concentrations as moles per liter. All right, and that's what the brackets, if it's in brackets like this, that is used to indicate moles per liter. Or in the case where we have gases like this, we could also express those concentrations as pressures as well. So two common ways of doing that. And so we could also, in this case, have expressed these, since they're all gases, we could have expressed these as the pressure of NO2 to the fourth, pressure of water to the sixth, pressure of the ammonia to the fourth, pressure of the O2 to the seventh. Okay, so another way, as long as the units that we use are all the same. Speaking of units, thing to realize on this is that the equilibrium constant K is expressed in a unitless form. Okay, so the key thing you need to be concerned with is when I'm figuring out a value for K, I'm either going to use all molarities or I'm going to use all pressures. We're going to use the same units to calculate it, but the value of K will not have a unit associated with it. Okay. Another thing to remember is that equilibrium constant is temperature dependent. So typically you will see a temperature provided anytime that they give you a value for K. That is just, even though you won't be using the temperature in the calculation, they'll provide it to you because that equilibrium constant is dependent on temperature. The other thing to remember is that the ratio is always constant for a given reaction at a given temperature. So the value of the equilibrium constant will be the same. However, there are often many combinations of reactant and product concentrations that will give you that ratio, and we call those equilibrium positions. That means it's a set or a combination of reactant and product concentrations that give you the value of K when you plug them into the equilibrium expression. Okay, some rules for equilibrium constants. Okay, one is that the equilibrium constant for the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. And the other is that when I multiply the equation for reaction, then that raises the equilibrium constant to that power of whatever I multiplied it by. Okay, let's do some work with this. Oh, also, when we're adding the equations, like when we were doing, say, Hess's law, if you remember way back then, where we could add equations together and the enthalpy for the overall reaction was equal to the sum of the enthalpies for the reactions you were combining together. Here, instead of a sum, it is the product of the equilibrium constants of all the intermediate reactions that's going to give you the overall equilibrium constant. Okay, so let's look here. Here I have a value for the Haber process, and it's missing its little arrow there. Okay, and it says equilibrium constant is 3.5 times 10 to the 8th. And we want to know what is the equilibrium constant for these other reactions, which are basically rearrangements of the original reaction up here. So what have we done to this first one? Well, we've basically just flipped it or written the reverse reaction. So K for this one is the reciprocal of that, of the original. Okay, and I'm not, for time's sake, I'm not going to calculate these out. I'm just going to kind of show you how we would get those. Okay, so now let's look at the second one. Here I have, what have I done here? Looks like I've multiplied through by 3. I've multiplied that one by 3. So K for this one is going to be my initial, and then since I multiplied through by 3, I'm going to raise it to the third power to get the new value of K. Then down here, let's see, what have I done here? Here I have reversed it and multiplied by 3. So it's going to be several ways to write this, but I reversed it, so it's the reciprocal, and then 1 over that, but then I multiplied by 3, so it's going to be raised to the third power. Okay? And then in this last one, let's see, I divided by 2. Okay? So but I didn't flip it. Okay, just divide it by 2. So dividing by 2 is the same thing as multiplying by a half. So it's just going to be the original raised to the 1/2 power. Okay? Okay, now one of the things that you'll notice is that you'll start to see these equilibrium constants with subscripts on them. And we use those when we are applying them in a more specific way. In this chapter, we're going to look at, you'll see them use K sub C, and that typically are, like you see in this diagram here, this is where they are referring to the values as concentrations. So if they give you an equilibrium constant and they say it's a K sub C, then that means that the values that they used to get that were the molarities. Whereas if they give you a value and it's K sub P's, then that would imply that they used pressures for that. Okay? Alright, so now, alright, what if we have one of these and we want the other? Okay? There is a relationship between the K sub C and the K sub P. And this is it right here. Alright, so the Kp is equal to the Kc times R, which is the gas constant in this form, times the temperature, which would be in Kelvin, then raised to the power of delta N. Delta N is sum of coefficients of the gaseous products, it's in blue, but I'm going to underline red, the gaseous products minus the sum of the coefficient of the gaseous reactants. Okay, so let's see what we have here. Here we're given a value, and a lot of times when they use K by itself, if they don't give you information to tell you if it's a Kc or a Kp, my experience has been that in a lot of textbooks, when they just use a K, that they intend that to be a Kc. Okay, they're usually pretty careful about if it's a Kp saying that, but oftentimes in the examples and the text problems, you'll see where it just gives you a value for K, and if there's nothing else to let you know differently, then just assume that it's a Kc. Okay, so here we have, and we're going to assume this is our Kc, and we want to know what the Kp is. All right, so what else do we know? We know that, oh, we don't have a temperature, do we? Let me see. All right, let's assume it's 25 degrees Celsius. Let's see. Oh, let me go back. Thought maybe it was going to give me a temperature, but it didn't. Okay, so we'll just assume that this is at standard temperature, 25 degrees Celsius, which is going to be 298 Kelvin. Okay, our delta N, what is that going to be? Well, the sum of my coefficients of gaseous products, well, my products is only the ammonia, so that's 2, minus the sum of my coefficient of gaseous reactants, which is going to be 1 plus 3. So my delta N is going to be 2 minus 4, or a minus 2. So Kp then is going to equal 3.5 times 10 to the 8th, okay, times 0.08206 times 298 raised to the minus 2 power, which is going to give me, let's see, 6 times 298. And I'm getting 323.4. Oh, wait a minute. No, that's not going to be right. Hold on. I thought that looked kind of odd. Okay. Scratch that. Forgot my parentheses. Let's see. 5, 8, 5, 2, 9, 1.9. Okay, which makes more sense. One of the things to realize is that if you have a really large K value, that implies that at equilibrium, we're going to have a lot higher amounts of products than we are reactants. So if you have K values that are, I think the rule of thumb is maybe 10 or greater, which in this case we have 3.5 times 10 to the 8th, that would imply that pretty much that reaction is going to completion. I mean, it's almost nearly there. If you have K values that are, say, less than 0.1, for example, then they really don't go very far towards completion. When you get to equilibrium, you're going to have a lot more reactants than you do products. Okay, so that's kind of a useful thing to remember about the K values is really that's kind of what they mean. They're giving you some information about how far towards completion does this reaction go, you know, when it reaches equilibrium under the conditions that you were determining these values. Okay, heterogeneous equilibria. Up to now, the examples we've looked at, we've either had all aqueous solutions in our reactants and products, or we've had all gases. So here we have, what do we do when we have more than one phase? Okay, one of the things that we have to remember is that if we have pure liquids or pure solids in our expression, that the equilibrium constant does not depend on them. Okay? And essentially what that means is that we have to have some of it there, like in the initial, this initial expression here, this first reaction. Okay, what we mean is that there has to be some of the calcium carbonate present and some of the calcium oxide present when the equilibrium occurs. However, the amount that is present does not affect the value of the equilibrium constant. So we do not include solids or pure liquids in equilibrium expressions. So let's look at, for this first one then, my equilibrium constant would just be okay. And then let's take a look at this one down here. Here I have the HCO3. Okay. And this second one, by the way, we're going to get into this in the next chapter, but if you notice, this is the dissociation of an acid in water. Okay. And we have, again, a special K for those, called as Ka, for acid equilibrium constants. And then down here, this is another one we're going to be dealing with towards the end, another type of reaction that has its own specific K value. But in writing the generic equilibrium expression, this would be the silver ions squared, SO4, the sulfate, there. Okay, this one, this reaction type, this is the dissolving of a solid in water. Okay, and you'll see later on that these are called KSP, solubility products. All right, and on these, the nice thing to know is that the calculations are much simpler because the reactant, which is a solid, will never be in the expression. We won't have to worry about it.